Hi, this is Dr. Tech recording his session about the practice exam number 2. This is, of course, I made this exam about a year or two ago, and at this point I have no memory whatsoever of, how to fix that program. In other words, I'm starting with a blank slate, pretty much like, everybody who's working on this particular program. The first thing you want to do is to take a look at the pseudocode and just kind of make sure that you understand what the structure of the pseudocode and what it does. And also, what is kind of important is the instruction of how to use the multiplication is listed up here. So that's one thing that you definitely want to do too, is to read it. The important part is the multiply instruction will store the product, the result in EAX and EDX. EAX stores the least significant 32 bits, and EDX stores the most significant 32 bits. It only takes one single operand, which is one of the numbers to be multiplied. The other number to be multiplied is in EAX, and that is implicit. Alright, so let's go ahead and get started here. Find factor, this program, even though it uses subroutine, I don't use any parameters. Everything is passed by global variables. And here we have all the global variables, f, n, x, y, GCF, and LCM. They're all global variables. And here, we have move. Okay, as somebody suggested, the first thing you can do is to move the comments around so that you can correlate the assembly code with the C code, and it's not too hard to do it. So I think you guys can pretty much do this by yourselves. I don't have to supply that to you guys. Okay, this is a plus plus f. Plus plus f is usually done by incrementing 1, and that is missing entirely. Well, wait, it's down here somewhere. Yep. Then we have the plus plus f, and we have the end of the loops. Okay, so I think we got enough to get started here. The first instruction is move L $2 to F. That's right. Okay, the width of the operation is correct. The type of the first operand is correct, and the type of the second operand is correct as well. Now we're moving on to the conditional statement. The conditional, not conditional statement, but the loop. The loop will exit when f times f is greater than or equal to n, or when n mod f does equal to 0. And the first part here is to double check and make sure that f times f is less than n. And we want to check and see if, let me use the line numbers so we can refer to the line numbers here. So we want to make sure that line 36 to line 38 implements the first part of the condition. We initialize EAX with f, and that looks right to me because f is a memory operand, direct, EAX is just a register, and the width of the operation is correct. And we want to multiply EAX to itself, and that's why EAX becomes the operand of the mul instruction, and that's correct. We want to find the square of EAX, and after the operation, EAX does store the result of the multiplication. EDX will be destroyed in the process, but since we are not using EDX for anything at this point, that's fine. We can afford to lose EDX. And then we want to compare that to n, and this is the correct order to do the comparison. And over here, let me just use a pointer here. This is jump to the end of the loop if EAX is not below n. If EAX, which is f times f, is not below n, so that is correct. This is one reason why we can get out of the loop. Otherwise, we go through the other parts of the code, which is from line 40 to line 44. Line 40 to line 44 tries to implement this condition here. Let's see if it is set up correctly. With the division instruction, EDX and EAX are the dividend, EDX being the most significant 32-bit, and this is correct. We want the most significant 32 bits to be 0, and we want the least significant part to be our dividend, which is n. The width of the operations are correct, and here we have we specify the divisor, which is f, and that is correct as well. The correct memory, the correct operands, and the correct width and then we have a division, and we compare the, in this case, the the remainder of the division, which is the mod operator. And if it is 0, we also go to find factor end loop, and that is correct. Inside the loop here, we just want to add 1 to f, and when it's done, we go back to the beginning, and everything seems to be correct here. When we're at the end, we have to perform the conditional statement, so let's go ahead and move that over here. So we want to copy this line to the first part of the conditional statement, and that would be here. And then we have the assignment operation inside the conditional statement, and that will be here. Okay. Well, let's see if that makes sense. We want to copy f to EAX, multiply it to itself, and then compare the square to n. And here, let me just read this operation. We want to jump to end if and only if EAX, which is the square of f, is not above n. Okay, so we have to reverse this operation here. If the square of f is not above n, we want to branch around it, and that is correct. Here we have move L and EAX, move L EAX F. In other words, we're just copying the value of n, which is this part here, to variable f, and that is correct as well. And that's the end of what we want to do, and here's a return. So it looks like find factor should be working for without any problems. And the first thing we want to do is to test find factor first. We don't want to do anything else until we get find factor done. And to find out how it works, we have to make sure that whatever number we want to find the factor of is in n, and the factor will be in f itself. Now to test this, we really need 2 test cases, and I'll put the test cases here. I just have to remind myself, begin of test code and end of test code. So this way I know which part of the program I should delete before I turn it in. And the first thing we want to do is to just initialize n with the other way around. Let's say we want to see if a prime number is recognized correctly. So we put this into n. We call find factor, and we want to define the label here, stop here. So when we return, we want to stop at this no op instruction, or stop here is fine too, and that's what we want to do. And let's see if the compiler or the assembler has anything to complain in this case. Oh, okay, we do have a few problems because of operand problems. So we have line 89, 101, 102, 103, 104, 109, da 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 da. We'll fix one thing at a time. Let's go to line 89 first. We have 2 memory operands, and we are copying it, from one to from one to the other memory operand, and this cannot be done because the move instruction can only have up to 1 memory operand at any particular time. That's fine. We just move it into EAX first, and then move EAX into X, and that should take care of this problem. Okay. And just comment on the instruction that you fix, so this way you know what you have done to the program. You can also use RCS too if you want to give that a try, so that you can easily compare between revisions of this program. Okay, that's the first one. I cannot remember the other ones, so I will run the assembler from inside the editor, just so that I don't have to get out of the editor. We have 103, 104, 105, 106. So 103 to 106 are all incorrect. 103, line 103 is here, and we have a whole bunch of mismatch of operands. So I would just say wrong width for operands may be fixed now, because all I'm going to do is to change the width of the operations so that the compiler will stop complaining. This is 103, 4, 5, and this is 6. We have to specify the divisor when we use the div L instruction. And we have to find out which one we are dividing. That depends on the um, the context. But I think in this case we're fairly sure that we want EBX, which is F, to be our divisor, because we want to divide it by the factor in the main code. So I'll say end of code suspected fixed now. Okay, all right, and I think that's parts of it. We have two more, too many memory references for move on line 13, which is the same thing, and line 118, no such instruction, da 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 da. Okay, so 113 and 118. Okay, let's go find 113. 113 is here, and it complains about two memory operands because EBX did not have a percent symbol. Now we don't really know exactly whether that will fix the problem or not, so we'll just say, suspected fixed. Now turn EBX into %EBX. So this is just a reminder to myself that I did make some changes here, and I suspect this change have fixed the problem, but there's no way for me to verify that correction at this point. And what is the other line? I cannot remember. Line 118. Alright, so this is line 118 here. It's a label missing a colon, and that's why it complains, because without a colon, the assembler will interpret it as an instruction. Okay, so let's go ahead and try to reassemble everything it did. Reassemble, and then we can do the linking. And it has an undefined reference to EBX. So let's go ahead and take a look at line 115. And here we have EBX, because it should be %EBX. And once again, I'll just say this is suspected. This is my suspicion that was the original problem. I'm not 100% sure this is fixed now, but that's my suspicion. So let's go ahead and give it a try. Assemble first and then link again, and then gdb x2 list the program. We want to stop at stop here. So b stop here. Run the program. And we want to take a look at F. F is 37. That's great, because the only factor of 37 is 37 itself. It is a prime number. It is a prime number. So the only other thing I want to do at this point is just to make sure that it can also find a factor of a composite number. So let's go give it a composite number. Let's say 35. It should find 5 as a factor. And obviously this is not the most efficient way, because I have to reassemble and rerun the program, but it's fairly quick. And take a look at F again, and F is 5. 5 is the first prime factor of 35, and that's great. The program is working at this point. And if I were using RCS, I would check it in at this point, because I want to make sure that I keep one version where find factor itself is saved. In fact, let's just do it. Okay, make their RCS, then we say check in and lock the file at the same time, and then we just have to exam question, and we are done. We checked it in already, and now we are ready to tackle the next subroutine. Alright, so let's see who is next. Our next subroutine is find GCF, which is a little bit longer, and we want to double check and make sure that the logic is correct. So the first thing we want to do is to copy and paste the comment, just so that we can correlate the code, the pseudocode, with the assembly code. Okay. And obviously we don't have to do everything, we just have to do enough of it that we can get started. Find factor is a call to find factor. Okay, there we go. And then after that we have a loop. And whenever we have a loop, we always have a label at the beginning of the loop, because otherwise there's no way we can find out how to get back to it. This is a division between F and X and F. So here we have the division. Let's see, what else do we have here? The original code, if y percent f. Okay, so here's another division, because to get to the mod we have to divide again. And let's see, that's our first division. And where's our second division? Aha, so we are missing something here. So something is definitely funky here. Okay, so I'll explain what I am suspecting. Here we have y gets y divided by f. Okay, y gets y divided by f is inside the conditional statement, so it goes here. Let's see what else. Oh, we have GCF gets GCF times f. We just have to find the mole instruction, and that will get us pretty close to the location of the code. And then we only have one thing else. Last thing to do is to restore x and y, and that is associated with the pop instruction. Now right here I can see there's a problem, because I have returned and then I have two additional instructions, and that never works, because after you return there's no way you can get to the instructions after the return instruction. So that's why right away I fix this one here. Okay, return should be at the end of the subroutine, like that. Okay, so now we have to go through a sanity check and see if the program seems to be at least sane. So we'll go ahead and give it a try. Save x and y, push x, push y, and we want to match the end exactly at this point. You can see that the order is reversed, because if you push x first, you have to pop x last, last in first out. So I spot that problem right away. And this is why sometimes you cannot just go for a linear scan of the code. You have to kind of jump around a little bit and see if the structure itself makes sense. Alright, this one is easier. Okay, we just want to copy a 1 to GCF. That looks right to me. As long as x does not equal to 1, we do the following. So we compare 1 to x, and if it is 0, we go to the end, because if it is non-zero, we stay in the loop. So far it looks good. And then we have n equals x, and you can see that this is probably not correct, because the order of the copying is incorrect, because we want to copy x into EAX and then EAX into n. So the order or the direction is wrong. Okay, fixed direction of copying. Okay, and then we call find factor. Very good. That part looks good to me. Okay, now we have while x mod f equals to 0, so we have to set it up for the division. Initialize the most significant 32 bits of the 64-bit dividend. Put x into the least significant 32 bits of the dividend. That's good. And f is our divisor. Now this time we have a little bit of a problem here, because percent f is actually the address of f. We don't want to use the address of f as the divisor. We want the content or the value of f, and the same applies to x. So here we have those two fixed. Okay, fixed immediate operands. They should be direct operands. Okay, and then we have a division, and now we're moving on to we have to compare that to 0, and we're comparing the remainder of the division, which is stored in EAX, to 0. As long as it is 0, we go to the end. That's not what we want. We want to stay in the loop as long as it is 0. So that means we want to get out of the loop when it is non-zero. Okay, so once I fix it, it becomes jump to end loop if and only if EDX, which is x mod f, does not equal to 0, and that's correct now. And obviously I would leave a comment here. Fixed JZ should be J and Z, like so. Okay, now into the loop, inner loop itself, we have x gets x divided by f. Once again, we have to we don't have to set up the division again, because when we calculated this result here, we have already performed the division. So at this point, when we get to this part here, EAX should still be the quotient of the division, and we can just copy that to X without having to divide again. Move F into EBX, and that's because we have to set it up to perform this calculation here, so this one belongs here. Okay, so now we want to divide y by f. Now this looks right to me, except for one thing. F is definitely our divisor, so that's right. Y is our dividend, and that's right. But we're missing one really important part, which is to initialize EDX, because EDX is the most significant 32 bits of the 64-bit dividend. If I don't initialize it, EDX will still be the remainder of the previous calculation. Now, it is true that in the previous calculation, EDX should be 0, because otherwise we wouldn't be here, because if EDX is not 0, we would have branched around. But it is always safer to make sure that it is properly initialized. Okay, and now here we have the divide instruction. And after the divide instruction, we want to compare that to 0, because if it is 0, we want to branch. If it is non-zero, we want to branch around the conditional statement, because according to the condition of the conditional statement, if it is 0, then we go into the then portion. That means if it is non-zero, then we skip around the body of the conditional statement. Okay, so that needs to be fixed, and here's my little comment saying that JZ should be JNZ to skip the then part. Alright, there we go. Okay, so now we have y gets y divided by f, and simply by copying EAX into f into y, and that's correct because EAX is the quotient of the division. The division happened on line 105, so it's already done. It's just that we haven't utilized the result of the division. And then the next line is GCF gets GCF times f. We put f into EBX, we put GCF into EAX, and these two will be multiplied by the mul instruction. And when it is all done, well, we have to do something before we go somewhere else, don't we? Because we have to store the result back into GCF. So it's time to move the result of the calculation, which is in EAX. That's the least significant 32-bit of the product, and copy that back into GCF, because otherwise, we finish the calculation, but it's not going to do us any good. And that's the end of the inner loop. Okay, let's double check and see if that is really the case. Okay, this is the end of the inner conditional statement. So I think this instruction is at the wrong place, because it is not time to go back to the beginning of the loop yet. Instead, we are at the end of the conditional statement. The branch instruction should go here. Now, once again, this is about the nesting of the loop. Because the labels of the names of the label really gives you an idea of whether the nesting is correct or not, because we were in a conditional statement and somehow we are branching out to a loop, and that really does not make sense. And this is also why I don't use the break instruction in C, because if I had used that, then it becomes possible to branch from a conditional statement into a label that belongs to the loop, and then I would not be able to spot problems like this. Okay, so let's see if this part is correct. Okay, we have loop and loop 2 begin. And let's see, find GCF loop begin, and this is the end of it. And that looks good to me, and that looks good to me. What I'm looking for is the name. Okay, this name should match this name here, because one is branching to the beginning of the loop and one is marking the end of the loop, and the same applies here. This goes to the beginning of the loop, and this marks the end of the same loop. So everything looks good at this point. My find GCF should be working at this time, and so I go back to my program and see if I can find the GCF of two particular numbers. And in this case, let's fix this and move L. Well, we can try something. Let's see. What should we try? Let's try 49. Okay, move 49 into Y. Their GCF, or greatest common factor, should be 7. And let's see if my program can do it or not. Well, of course, change the subroutine too, because otherwise, obviously, it's not going to work, right? And now we have find GCF. And run the program. Oh, segmentation fault. No. Oh, compare 0 to EDX. Well, these are easy problems to fix, because the segmentation fault happens exactly at the wrong instruction, or the instruction that is incorrect. So that makes it really easy to fix. The worst kind of problem is when you have a problem that happens much earlier, and then it doesn't show up until much later. But in this case, it's quite easy to fix. Go to line here. And we can also spot for similar problems, but we don't have anything else already at this point, so we're good to go. Okay, assemble, link, and GDB again. Once again, put a breakpoint at stop. Whoops. Stop here, and then we run the program and print. What is it again? GCF. GCF is 7. Great, that works. All right. Now let's go change the program just a little bit, test yeah, this is not the most efficient way to do it, because I should have put a label here so I can just change X and Y and then run it from within the program again. But no, I'm too lazy. Okay, and then we do the same thing. We put a breakpoint at stop here. Run the program, print GCF. This time it should be 1, and excellent, that works. Okay, one more case to test, because we want to see if one number can be the GCF, the entire number can be the GCF of another number. Let's try 35 and 70, because 35 should be recognized as the GCF of the two numbers. So let's go ahead and give that a try. And that worked too. Excellent. Alright. So I'm fairly sure that the program is working up to this point, and it is time to move on to the last portion, which is the implementation of find LCM. Alright, so we just have to check that part, and by the time we are done with find LCM, we don't need the test code at the beginning anymore. So here we go, find LCM. We want to call CALL find GCF first, and once we find GCF, we want to find the LCM, and we just have to go through the calculations. So we have to move LX into EAX, which is the least significant 32-bit of the dividend. Move L0 into EDX, which is the most significant 32-bit of the 64-bit dividend. And then we want GCF into EBX, and then perform the division instruction using EBX as our dividend. And then the quotient is stored in EAX, so we can reuse that. We just have to specify Y as our other number for the multiplication, and then perform the multiplication instruction, and then the result is stored in EAX and EDX, but EAX is the least significant 32-bit of the product, which is the only part that we care. We don't really care much about EDX, which is the most significant 32-bit of a 64-bit product. And it's time to move just EAX into LCM, and I think that should be it. Alright, and we don't need the beginning of my own test code anymore, so it's time to get rid of that. And at this point, we can stop at checkpoint 1 and see if the result is correct. I think in this case what is the largest common fact multiple of 36 and 48? Well, I guess we'll use the program to find out, won't we? Assemble, link, and GDB. Put a breakpoint on checkpoint 1. Run the program. Print GCF first. GCF is 12, which is correct. And then print LCM. LCM is 144, which I believe is correct as well. Because we can always, do the calculations here. We can always say what is 36 divided by 12 times 48, and the result is 144. So, hooray! The program is working. If you have time left, after this, you can give it more test cases, just to double check, make sure it works on, the trickier, cases. I suspect it's going to work, because the trickiest part is really to get GCF to work. Once you get GCF to work, LCM just relies on the result of GCF. There's nothing, there are no conditional statements, and there are no loops in find LCM. So the chances of messing up LCM so that it works in some cases but not others is not really that high. The probability is pretty low. And here we have it. It's all done. And after this, you just have to turn it in, archive the whole thing and upload the file to Moodle. And that's it. All right. Well, thanks for watching. If you have any questions, we can talk about that either today, which is Thursday. But some people may not have read this or watched this video by tonight. So if you have any questions, just send me an email. If it is a common question that I receive from multiple people, I'll just go ahead and post another YouTube clip to address that. Well, anyway, thanks for watching, and I hope you find this little exercise at least a little bit interesting. Okay, bye.